Okay, so let's go ahead and get started. First, for those of you that are joining or have just joined, please make sure that your microphones are muted, so we don't have any additional unwanted sounds. Let's get going here. So today it is my pleasure to welcome Dr. Lorenza Viola, or Professor Lorenza Viola. She is actually part of one of our art projects on Team, and she's here today to talk about some of her recent work. So Dr. Viola received her PhD in theoretical physics from the University of Padua in Italy in 1996. After that, she did a postdoc. She's a postdoctoral fellow at MIT until around 2000. And then after a J.R. Oppenheimer fellow at Los Alamos. In 2004, she joined the Department of Physics and Astronomy at Dartmouth College, where now she is a James Franck Family Professor of Physics. And she's been at Dartmouth ever since. So today she's here to talk to us about simple problems in open quantum dynamics, from dissipative quantum encoding to quantum noise spectroscopy. With that, Lorenza, I hand it off to you.
Thank you, Greg. Let's see. So we don't want to have that. Full screen. Thank you, everyone, for coming, and I hope you can hear me fine. My computer should be going full screen.
There you go.
There we are. And let's see. No, I don't want to do that. Can you see my little hand if I move it around?
Yes.
Okay. Well, okay. Without further ado, let's get started here. And thank you. Probably, let me see if I get rid of this. Okay. Those of you who know me won't be surprised to hear that what I will talk about has to do with open quantum system dynamics. Please ask questions as they come along. I don't necessarily expect every one of you working in open quantum dynamics, so I would nevertheless give a couple of slides of context to put this in perspective. So the grand challenge, I would call it here, is to achieve control. And by control, I have a pretty broad system theoretic definition by which I include stages of characterization, identification, modeling, as well as optimization. So you can say it's a pretty, multi-stage process in itself. We would like to achieve that for realistic open quantum system dynamics. And it's kind of funny, we talk about in open system, we definitely have a target system of interest, and we have an environment in open dynamics, nevertheless, always. Green in my slides, as always. But it's kind of interesting that for a long time now, I would say that two different yet coexisting philosophies have been used and continue to be used in the field. So I said we have a target system, that the target, for instance, computational system of interest. This is interacting with an environment, but the environment, notice that I have kind of divided up into two subsystems in themselves. And these two subsystems, A and B, they will have a physical meaning of one of them providing, let's say, a physical, like uncontrollable, very often also inaccessible contribution to the dynamics, so like an uncontrollable subsystem. The other instead is more of like an auxiliary subsystem, which is under our control to some extent. So with this in mind, the two philosophies I was alluding to before is one The fact that the system doesn't evolve unitary, it's open, is kind of like a curse. It's a bad thing because the coupling to uncontrollable degrees of freedom induces unwanted non-unitary effects, which can happen at either the Hamiltonian or analog or the circuit gate level. We are in NISQ era, but this is not only relevant for NISQ scale devices, it's going to be very well relevant beyond. In this case, the role of control is one of coming up, providing means for noise mitigation, so identification and rejection. And something that I would like to emphasize is that these various strategies can be devised at different levels of characterization of the environment that might be available, meaning, for instance, if we wish to have a strategy which is pretty model robust, so it requires only limited knowledge, this is possible. For instance, dynamical decoupling techniques have been developed in the early days solely based on knowledge of, let's say, symmetry properties of the interaction between the system and the bath. But as soon as we try to push the control towards, like, let's say, optimal performance, then the characterization of the degrees of freedom that we wish to control will have to become correspondingly more detailed and quantitatively accurate. So there is this kind of tension between model robustness and optimization relative to the noise. So the other philosophy, let's say, is one where instead we are turning attention more to the other subsystem, which is part of a general environment, and we are trying to see the openness of the target system as a resource, in that having access to controllable quantum degrees of freedom enables engineering of a target non-unitary dynamics on the system, which can happen in discrete time in terms of a quantum map or channel, or in continuous time, for instance, in terms of master equation. With this in mind, the role of control becomes one of quantum reservoir engineering. And there are some of us who like to joke, instead of thinking of NISQ era, we talk about DISC era, in the sense that we can think about a lot of dissipation assisted or dissipation enabled quantum tasks. I would say, from a theoretical perspective, the general system theoretic framework, let's say also the full scope of dissipative control, remain still these days less developed than they are for the unitary case. So with this very broad arena, clearly irreversible quantum dynamics and open quantum engineering is a huge field. I have followed this field for many years now, motivated by a number of questions that range from providing robust realizations of both quantum storage and processing, for instance, working decoupling, dynamically corrected gates, working characterizing noise effects, both for boosting the performance of quantum devices towards, for instance, fault tolerance, but also to gather fundamental understanding about noise physics, all the way down to more let's say, problems at the intersection between quantum information science and condensed matter physics in terms of figuring out how to use control to engineer maybe state of matter that wouldn't exist otherwise. What I have decided to pick for this talk is to, like I had in my title, sample problems, so to speak. And I have been fortunate enough to be in some way part of both efforts, both the FARQC and the team award. And so I have picked two tasks. one having to do with dissipative engineering, and more specifically, dissipative preparation of resource quantum states at the encoded level. So the problem at hand has to do with specifically encoding stabilizer quantum codes by means of engineered Markovian dissipation in discrete time. And then the other task, which is instead more specifically related to what we are doing with Tim, has to do with characterization of unwanted noise effect through the use of qubit sensor, which has to do more specifically with spectral estimation or quantum noise spectroscopy, as we have become familiar and calling it, of no longer Markovian, but now temporally correlated, or in this context, non-Markovian, non-classical noise by using control, which in this case instead is continuous time and is inspired by spin locking techniques in NMR. So let me get started with the first of these topics. This is a problem that actually originated when Peter Johnson used to be a graduate student in my group, and only very recently have we, however, completed the necessary steps to bring this to fruition, together with Francesco Ticozzi and Giacomo Baggio, both of them being in Padova. Since I will not go over technical details and particularly proofs at all, for those of you who might be interested in, this is the publication that was coming up not too long ago. So maybe I can just say that, not to take credit which I don't deserve unnecessarily, non-unitary control engineering has existed for a long, long time. Perhaps it dates all the way back to mid-90s to the idea of reservoir engineering by Poyatos, Dirac, and Zoller. It has been used a lot in quantum computation to confine dynamics, for instance, to decoherence-free subspaces. I would say that from the point of view of quantum control of open quantum system, for me, it's been a very long-standing interest. And this is very old work I did with Seth Lloyd back in 2000. And that's where we first show how the use of the smallest auxiliary quantum system, namely a single qubit, as long as it could be resettable, could be used for universal approximate simulation of arbitrary quantum dynamics on a finite dimensional quantum system by, I heard something, by using only unitary control in addition, as well as discrete time feedback. So this, of course, has been used later by other people. My computer is behaving, is going back. Okay, and has been translated into circuit implementation for open quantum system dynamics. Many other applications have emerged for using engineered dissipation, for instance, for efficient quantum state preparation. And something that caught my attention was recent work in the context of the FARQC effort by McKenna and Mohan Sarovar, where they also use open quantum system engineering to design thermal Gibbs states as unique state fixed points of the dynamics. This is something that will resonate with what I'm going to mention very, very soon. So long list of applications. Closer to what I will talk now is the idea of using dissipation to get quantum memories, to get autonomous quantum error correction. Like I said before, however, applications of dissipative dynamics have also emerged and have emerged for preparation of strongly correlated topological quantum phases of matter. And I think that there will be more that we're going to see at the intersection between different fields. I couldn't resist to put up and say that we also had very recent work in this cross-disciplinary arena, and that's one where we actually use dissipation to bring to the fore non-trivial topology in non-interacting bosons. So with that, I think I should also mention that dissipative engineering is not just a theoretical endeavor, but it is becoming an increasingly prominent reality in different experimental platforms, and a lot of experiments are coming up as we speak. But let me finally zoom in and come closer to the subject that I wanted to tell you about. So I said that we want to talk about using engineered Markovian dissipation to, let's say, generate resource encoded quantum states. This fits into the broader task of quantum stabilization, which is to say designing open system dynamics such as the target manifold of interest, in the case that Tandy will be a quantum code, is globally asymptotically stable. So it arises as somehow the unique attractor of the dynamics. So these are all publications that we have had. This is a problem that in various ways we have studied over the years. And you might wonder what are advantages of unitary as opposed to dissipative state preparation or stabilization. Now, of course, there is no single winning strategy. It depends what the figure of merits and what the interests what, let's say, the important features are. But some advantages I can think of certainly is the fact that because dissipative control is not one-to-one, but it permits all-to-one control laws, the need for precise initialization of the target system is bypassed. Likewise, if one ensures that the dynamics evolves in such a way that the target manifold is the unique attractor, it is possible to have transient disturbances or noise effect to be reabsorbed naturally by the dynamics, which is one way in which autonomous stabilization or correction is being intended. Another feature which is advantage is that if the target manifold is invariant under the evolution, well, once it is reached, then no further dynamics happens. It is invariant, as we said, and so there is no need for active intervention for maintaining the desired manifold so that it can be accessed on demand. So with this, one might wonder, well, all of these advantages to a lesser or greater extent have been realized. They are clear for a single state of interest. But what about having a more complex task like a manifold, which has to be a quantum code? And interest in this direction has also been triggered when we were looking back in the years by a paper that appeared by Dengis, Koenig, and Fernando Pastavsky. As you can see, they have a proposal for an optimal encoder based on Markovian continuous time Lindblad dissipation for a particularly relevant code, which is Kitaev toric code on the square lattice. Now, the question that indeed I wanted to answer is like, well, what class of codes can be dissipatively prepared according to Markovian dynamics? And in particular, since we now know that if we consider Markovian dynamics, which is discrete time, so it's a sequence of CP-TP maps of quantum channel rather than being a continuous Lindblad dynamics, it is also possible for an attractor to be reached exactly in finite time, well, is this possible for codes? Yes or no? Because if that would be possible, then it would mean that under ideal condition, we would have convergence in finite time with zero error. Whereas the convergence that Lindblad Markovian dynamics can give in practice, because we cannot wait infinite time, is always going to be approximate. So with this question, let me just refresh our memory on what actually we are talking about. A quantum code, the way I mean it here, is a representation of abstract quantum information that is carried by an ideal logical system, and it is going to be carried into a physical system, and the map that achieves this encoding has to be such the code indeed has some desirable properties. For instance, it could be a noiseless code, it could be correctable, protectable, unitary correctable. There are lots of different codes. Indeed, we also know this is the so-called subsystem principle in error correction theory, that every possible faithful encoding of quantum information has a subsystem structure, which means that we see the information carrying system as we see that as a tensor product between a system where the information will reside, tensor, the cofactor, plus a summand in the most general case. We also can say, without that for sure, that the simplest case in the family of codes is one where actually we don't have a cofactor system, in the sense that it is isomorphic to just the complex field. And so the space in question can just be mapped as a direct sum, as you see it here. And so the goal of the encoding that I have up here is to map a desired state into the system contribution with nothing, with no amplitude into the summand. So I will focus on a particular but physically very relevant class of code, which is stabilizer quantum codes, and I am viewing them on as subspaces codes, indeed specified as the common +1 eigenspace of a stabilizer operator set. These are going to be R, let's say, mutually commuting stabilizer operators. These are elements of the Pauli group on M qubits. I will consider qubits, not qubits, in what I'm saying. They have to obey these commutation rules, and as you can see, they stabilize in the sense that states in the target code, they have to be belonging to the +1 eigenstates. Now, a stabilizer code will be able to encode a number n-r logical qubits, and logical degrees of freedoms are going to be specified by corresponding encoded observables, the choice of which in general is highly non-unique, but something that every possible choice of encoded observable has to obey is the fact that they have to obey Pauli algebra properties to represent valid qubits, and my logical observable are with bars, and also they have to commute with all the stabilizer generators. So, so let's look a little bit more carefully at what the task of encoded quantum information in the code actually is. And I like to decompose this into two steps. And there is also like a picture that I've tried to draw here to clarify what I mean. So there is a first logical encoding step, or simply speaking, initialization, where, let's say, the abstract information that we wish to encode, say it's a quantum bit, is or 2 quantum bits, is uploaded in some physical degrees of freedom. It could be some physical spins or pseudo spins that are easy. It's it's easy to put it there. However, it doesn't mean that once in these physical degrees of freedom, it doesn't yet mean that it will be, for instance, protected against noise. Then, once the information has been put there, the actual physical encoding step, which takes that physically realized information and moves it from a place where it is not protected, for instance, to the intended physical state, that is what I will refer to as a physical encoding or encoder. And the overall encoding protocol is can be thought as the composition of the 2 steps in this way. Now, having clarified that, in the standard quantum circuit gate-based model, it's the physical encoder that we think is usually realized via a unitary quantum circuit. So what it means is that that map, that phi p, will take the general subsystem structure here and map it via a unitary circuit to the intended space plus the cofactor. I will ignore the cofactor pretty soon, but for generality, I still had it in this expression and nothing in the rest. Now, like I mentioned a couple of slides ago, this requires, think about, for instance, if you wish to initialize a quantum repetition code for a single qubit, you have to initialize whatever non-upload qubits into a specific known state. Otherwise, the unitary encoding will not work for sure. So this requires, in general, precise initialization of physical qubits, unless, for the sake of completeness, I should say that for a number of codes, they can also be realized in the context of operator quantum error correction. And if they exhibit gauge degree of freedom, then some additional robustness against initialization might be possible. But this is not the generic case. And also checking whether a given implementation has or has not gauge symmetry is not trivial. So the question that I would like to explore is, if we allow specifically Markovian dissipation to be the dynamical steps that achieves the physical encoding, could it be that we can have additional robustness in the initialization of the code itself? Like I said, a key feature of dissipative dynamics is that it has many to one, not one-to-one. So this means that the basing of attraction, the set of possible initialization that gets attracted into the code can be non-trivial. And this is where the origin of possible additional robustness might come. So I will define with this a dissipative encoder. And like I said, this is the physical contribution of the encoding, one that when concatenated with the logical step achieves again the intended mapping. And I am going to say that, and this is the new picture to have in mind, that this will tolerate a faulty initialization, which I am modeling as if I have the ideal initialization followed by a noise map, if it will be able to achieve the intended encoding nevertheless. So whether or not the map N is present, we will say that the encoding is noise tolerant if it's able to achieve the mapping of the logical contribution into the right place regardless. So I already mentioned I am interested in Markovian dynamics. It can be, in principle, continuous time, like it was in the work by Pastavsky and collaborator that I mentioned before, in which case the definition is we are going to say that the encoding is dissipatively achieved if in the asymptotic time regime this condition is obeyed. More interesting to the discussion at hand will be the case of a discrete time encoder where the encoding is achieved via a sequence of CPTP maps. And this sequence can still be infinite, but for the case of discrete time dynamics, and only for the case of discrete time dynamics, it is possible to show that under appropriate condition, one can also ensure convergence with a finite number of iteration or application of maps. And that's what we call finite time convergence. For any control theorist in the audience, this is sometimes referred to as deadbeat convergence. Don't ask me why. So the strategy for constructive finite time encoders for stabilizer codes is going to involve a number of steps. And at the very minimum, what we need to ensure is that we need to correctly prepare the code space. To do that, we are going to choose encoding maps that in some way are reminiscent of the error correcting operation that the stabilizer code itself is designed to handle. So these are the maps in questions, and these A plus, A minus are constructed like you see. The meaning of this is that these identity plus minus SK, they check if the state would be in the +1 eigenstate, so it will be in the stabilizer code. If it is good, no action will be needed. If it's not, and this is why you see it with the minus, if not, we apply the unitary correction that the stabilizer code would demand. But these A plus and A minus are, as you see, appearing as Krauss operator into a quantum channel. Now, with this, it's possible to prove that provided, and this is one condition, provided this correction operator C obeys anti-commutation with the stabilizer operator for equal index and commutation relationship with different indices, then any concatenation of the maps, and notice I have phi 1 to phi r, r in my notation was the number of stabilizer generators. This prepares the code subspace, and further to that, each encoded state is left invariant under the action of the map. That, however, is not enough for saying that we have achieved encoding, because if we want to say that we have achieved encoding from a given physical system into the code, we need to ensure that the qubit structure, the upload qubits, are mapped correctly. This is where we took some time to figure out how to get it right. And with insight, the most natural thing to do is to shift to the Heisenberg picture and actually require that the encoded operators, they kind of are extensions of the upload ones, in the sense that they are seen as completing, in my notation, n minus, so r is the number of stabilizer, and n minus r is going to define how many encoded qubits we will have. So essentially we are demanding that the encoded observable here, they match the upload ones to the extent that is possible, and then they complete them with suitable properties on the remaining cofactors. So with the appropriate conditions, which I have put here, which have to be invariance condition in the dual Heisenberg dynamics, the results that one can prove is that if we take any stabilizer group, which is associated to a code, a stabilizer code, it is indeed possible to come up with a set of generators, logical operators, and correction maps which obey all these, I'm sure, pretty obscure mathematical conditions that I have put up, but that altogether make it possible for a finite time dissipative encoder to be realized. And furthermore, a byproduct of this construction is also that, number one, the order in which we apply these particular maps that we can construct in the proof of the theorem, the order doesn't matter. So we have a robustness with respect to the application order. And provably the basing of attraction is characterizable, is always non-empty. And it is characterizable as a +1 eigenstate of these R operators, which come up as Pauli strings on the cofactor here. So there are a lot of examples that we have looked at, and including the toric codes. I have it here, but I will not try to go into the toric code because it is, I think, too technical. But let me say that, for instance, if we look at, let's take a standard, but still quite powerful code, which is the 5-bit code. The 5-bit code is the smallest one, which is non-additive. It's probably the smallest one that can correct for arbitrary single qubit errors. It clearly is designed to encode one logical qubit. The code words are given here. And the choice of stabilizer generators in the standard forms, we have 4 of them. So 5 minus 4 is 1 logical qubit. And my choice of encoded observables is given here. With this choice of coding of encoded qubit observables, a set of those correction operators, which I will use into constructing, and the number of maps that perhaps this was too fast here, but the number of CPTP maps that enter the construction of this encoder is R, the number of stabilizer operators. So these C's are the ones that enter the construction of these 4 maps. And importantly, the basing of attraction, what does it mean? The basing of attraction is the set of initialization, which if one is able to put the system in there, one can provably have them converge to the code. It's important that the basing of attraction include some product states, because these are the easy one to prepare. And it does, for instance, include like the 0, 0, 0, 0. We can always ensure that the product state is included. Now, I picked this example because in this case, the dissipative encoding protocol that we have can tolerate arbitrary initialization, so to speak, on as many as 4 of the qubits, which is quite remarkable. And it can tolerate, let's say, faulty initialization so long as these conditions here are obeyed. In contrast, unitary implementations of the encoding circuit for this code, they are not known, to the best of my knowledge, to have any gauge symmetry, so no robustness against initialization errors is achievable via unitary encodings. So like I promised, I had the toric code. We can analyze it as well in this scheme, but I realized that I would like to also tell you something else about the other problem. So if you are interested in how the exact construction of a dissipative the finite time, in this case, encoder this is, like I said, the toric code on an L is the square Kitaev code, the ground state of this stabilizer Hamiltonian. It's a 2-bit logical topological code, if you want, is the simplest one, topological code we can think at. And the reason why it would be a little bit tricky for me to explain in detail how this works is also because what we had done is to examine the continuous time dynamics and then realize, which is what these pictures, which I'm not sure you can see, but there are some numbers here. So 1, 2, 3, and then 4, 5. You see, there are numbers here, which we came up by examining the continuous time encoder and noticing that that was in fact suggesting a particular choice of ordering for the dissipative map themselves for finite time action to be achieved instead of the asymptotic one that the previous one was realizing. So the upshot is that, yeah, this is still a stabilizer code. The fact that it is more complex, it is topological, doesn't prevent the general results to be applicable. And as you will see in my conclusions later on, one outstanding question is, well, these are stabilizer codes. What about more general codes or subsystem codes to begin with? So I will leave that for later. And if I can take, do I have like 10, 15 minutes, Greg?
Yes. Yeah, you have 10, yeah, until 3, yeah, until 3. Can you hear me?
Yes.
Yes. Okay, yes. Yeah. So until 4, but I guess yeah, I think another 10 minutes should be fine.
Yes. So I just wanted to switch gear and at least say where we are with, I think many people are familiar with quantum noise spectroscopy, if not have done work directly on them, and at least mention what we are up to in that context. So we are switching gear here. We are going from the Markovian world where we engineered dissipation, and that's truly non-unital dissipation, I should say, something that can achieve cooling. We are switching to non-Markovian temporally correlated noise, and for the time being, it's meant to be noise that is adversarial and therefore noise that we wish to characterize so that we can achieve optimal performance in control or error correction or the like. Now, as you can see, why I like to always start saying that we still need to characterize noise, because after many years of investigation and effort, the understanding of quantitative noise mechanisms is still not complete. And the Poynting case was offered by work on charge noise in superconducting qubits. I like to mention this paper, but for the sake of going a little bit faster towards work that we have done, let me skip. Let me also go quickly on the fact that, yes, like I said, one reason why we need to know noise properties that, for instance, computational degrees of freedom experience is because only with quantitative knowledge available can we hope to devise noise tailored and noise optimized error correction routines or optimal control routines or error mitigation routines. And we know that this is going to give substantial benefit. The reason we know why, if you wish, I have this single picture here, is because even simple, for instance, protocol for noise suppression, such as decoupling, which are not yet optimized for particular noise environments, such as CPMG sequences, they are offering improvement, and this is taken from a recent paper from the IBM team, where they were showing that they used the application of decoupling during idle periods was giving improvement being quantified by 78% of these points being above this line in this picture. So we can only, extrapolate that by optimizing for particular noise environment, we will further boost the performance more. So with that, and maybe this is a very dense scheme with more motivations for quantum noise spectroscopy as part of team and beyond NISC, and also with implication for metrology, let me come and talk more specifically about quantum spectral estimation, noise spectroscopy, which comes in many flavors. Essentially, the goal here, and let me focus on non-parametric estimation, where we really wish to estimate for instance, in the frequency domain spectra of the noise process that affects a given system. Well, if we focus on that, there are a lot of possibilities depending on how the control is implemented to drive the sensor, so that the control sensor's dynamics will, once appropriately deconvoluted, provide information about the noise itself. So the control modality could be in the form of narrow pi pulses. And so lots of effort has happened and lots of experimental implementation have been achieved on so-called dynamical decoupling noise spectroscopy. There is also a lot of work and beautiful work that, for instance, Lee and I did together when she was here at Dartmouth on using Slepian, and that she's continuing now on Slepian modulation for achieving optimally band-limited noise spectroscopy. The one I will focus on is, like I said, more inspired by NMR, and has to do more with continuous modulation of the sensor, and with the possibility to use either a single or multiple sensors. So let me talk briefly about 2-qubit QNS. In that case, we would have two target sensors which can experience both, that can experience noise both independently, but also in a correlated fashion. And if we imagine, for the time being, let's imagine that the noise that the system experiences is single axis, is dephasing noise, then the target of a noise spectroscopy protocol becomes one of estimated a family of spectra, which I have indicated here. They are labeled by two spectra. They are Fourier transform of Bath autocorrelation functions. And in general, we can have, like I said, self spectra, individual qubit ones, but also cross spectra, which encapsulate noise correlations. These spectra need not stem from classical noise processes. So in general, we might expect the distinctive non-classical nature of the noise process to imprint itself into special asymmetry properties with respect to either zero frequency, if we work at dephasing noise, as I am considering now, or more general with respect to driving. So what is the concept, the idea of spin locking QNS? Well, I said that we have dephasing. I mean dephasing in, let's say, a laboratory system, but spin locking is based on the notion of driving the system off axis. So say that we apply a coherent drive, for instance, along an x direction of axis, And by doing so, we are effectively tilting the quantization axis of the original system. And we can think of the driven dynamics as if it would arise from a new dressed qubit system. And if the angle of the tilting is made into like a 90 degrees, then what used to be dephasing becomes transverse X noise. And so what used to cause dephasing noise causes emission and absorption. And we can hope to probe that at the drive at a frequency which is depending upon the drive frequency, and the drive frequency will be tunable, which will allow us for sampling the spectrum. So this idea, which I have alluded to in the case of one qubit system, actually generalizes to two qubit systems. And that's what I am what I'm doing in this cartoon here. And the resulting spin locking dynamics under suitable weak coupling assumptions can be described still in a non-Markovian way, but through a local time convolutionless master equation, which importantly includes the target spectra as, let's say, coefficients ruling the processes of correlated emission and correlated absorption that the noise can induce. So with this setting, then the problem of extracting the spectral information becomes essentially, although a complicated one, but essentially in spirit a problem of nonlinear regression, because it's a matter of figuring out how to suitably initialize the system, what suitable experimental observable to measure, so that via appropriate nonlinear regression, we can globally minimize the deviation of model versus observed data. And this is a protocol that we worked out and proposed. It doesn't require any entanglement between the qubit nor entangled measurement, only preparation of product states and simultaneous qubit observables. It has been successfully, I would say, implemented by our MIT colleague with 2 transmons qubit. I will not go into details in saying how, but I would just like to say it was implemented, but not on native noise, rather on engineered photon shot noise in a cavity. It was still very instructive, and certainly here are the experimental results, a necessary step to, let's say, calibrate, benchmark the protocol. But next steps that we would like to get to with noise spectroscopy would be towards really assessing native noise sources in existing NISC and beyond platform. This brings me really to the last current topic that I want to touch upon. Is just 2 slides, but it is what we are doing now, and we are still collaborating with, this is part of team effort with Lee and other colleagues at APL. And now the team at Dartmouth comprises my grad student, Kasib, and the postdoc, Wenzhen. So in order to make noise spectroscopy protocols more applicable, there are many, improvements to make, but one kind of pressing issue is the fact that as the strength of the noise to be sensed become weaker, and presumably that has to be the case if the NISC device is good enough for high fidelity performance, then all the more important do state preparation and readout errors become. And in fact, it is known from, for instance, experiments in existing IBM Q devices that readout errors are substantial. They can be up to several percent per qubit. So clearly this would substantially bias and distort the reconstruction if we were not to properly compensate for that. So what we are working on is to suitable modification of spin locking protocols so that the estimates that we can get are spam insensitive. I have mentioned here the concept, just imagining that we still have dephasing noise, but in reality, the protocol we have is extendable to arbitrary like dephasing and depolarization. So we can allow for faulty initialization in a mixed states with an error, let's say epsilon, that turns out to impact observable expectation in this way. We can account for faulty measurements by introducing faulty POVMs relative to the appropriate measurement basis. Again, it turns out that the errors introduce a scaling factor in the relevant observables. I have only X observable for the dephasing case that I am considering here. So upshot is that we have scaling factors that are introduced by spam. So how to modify the protocol in such a way that we can get estimates that are spam insensitive? Well, I know that time is very short. It's easy for the classical contribution to the spectrum because the estimate of the classical contribution to the spectrum might be directly expressed in terms of the spam affected estimates. And so we can get a linear fitting problem without too much trouble. It is a little bit less trivial, but still possible to infer, and this is a typo, this should be an S minus, not an S square, but it's possible to still extract, knowing the Spamfree estimates for the classical spectrum, is possible to extract Spamfree estimates for the quantum spectrum as well. And something that I find very interesting is that because in spin locking protocol, we look at long time dynamics, but we also, long time doesn't necessarily mean asymptotic. So we can have access to both the long time and the asymptotics if the noise, and only if the noise is quantum mechanical, so it's non-classical, non-commuting, we have a way, as it turns out, to separately assess the state preparation and the measurement errors, which, to the best of my knowledge, we don't know how to do in other ways. So,
hey, Lorenza.
Yeah.
Hey, Lorenza, we're a couple minutes over here.
I'm done.
Okay.
Yeah, as you can see, is really the last thing. I had the demo results produced by Kasim for classical noise. And like I said, the analysis and the protocol, they can be extended to multi-axis noise. And really, done, I mean done. I was just repeating that I really like to say that the niche scale type of open quantum dynamics we are facing, it gives a lot of challenges, but also a lot of room for new methods, new ideas, new protocols for being, put forward, both in unitary, but also in dissipative settings. And the rest is just a memo for you to read. And with that, I would like to stop. And thank you.
Thank you. Thank you for the nice talk. We are over here, but if there is one quick question.
One quick question? Okay.
We
Oh, okay. I didn't know it was so tight. I'm sorry.
It's fine.
I thought we started 5 minutes late, so it's like, yeah.
Yeah. No, I know. Any questions? Okay. I guess you had answered all the questions already that people had.
I doubt about that.
Yeah. Quick question.
Alireza.
Yes,
Hi.
Alireza, go ahead.
Go ahead.
So in this, when you apply this spin lock drive, you're showing a Markovian non-Markovian master
Non-Markovian.
equation.
Yes.
But just wanted to confirm those, that S of omega minus omega, those are, was it S? So those are time dependent, right? There should be a time dependence somewhere. I just couldn't see it.
Let's see. Don't think there is these ones.
Yeah,
That's
so
a master equation.
Yeah, so the generator L, like
L
calligraphy
rho.
L, is there any time dependence in there or no?
It is expressed in terms of frequency. No, it's not time dependent.
Okay.
This is in the frequency space. I know what you're thinking. You are thinking to the fact that we have inhomogeneous time inhomogeneous dynamics, or like the fact that I don't know.
Yeah. So if that is just a scene, that's just a number, then how can I see that it is non-Markovian? If those are also positive?
Wait, I am not saying, so this is going to be, so the structure here is structurally akin to a Lindblad, right? But these are not providing positive semi-definite. They are not even real numbers in general, and they are function of frequency.
Okay.
So, yeah, if you were to look at this same master equation in the time domain, like for a non-Markovian spin boson model, you would get, I mean, like the coefficients would be the time derivative, for instance, of the decay, chi of t derivative. And that would be Markovian only in the time interval during which that would be non-negative.
Okay, so there is I have to go to the time domain and then we see the structure that we are.
Well, here we wanted to express this directly in terms of the spectra because we wanted that to be our model dynamics for the sensing part. I should say the TCL master equation is a textbook tool, so we have just adapted that to this setting. So I mean, we can exchange emails and I can follow up more on that.
Okay. All right. Well, thank you again, Lorenzo, for the nice talk.
Sure.
As somebody had asked about whether or not the talk is going to be available, so it will eventually be available. Yeah, thank you all for joining us, and we will see you next month. Thank you again, Lorenzo.
Thank you. Bye.
Bye.